if you go to the store and get a half dozen cookies, you have 6 cookies. Does that make sense? So let's say you wanted 3/4 of a dozen eggs. Then you would have 9 eggs, because 9 is 3/4 of a dozen, which is 12. So if you don't believe me, type in 12 times 3 divided by 4, and you'll get 9. So when I ask how much does 0.208 moles of CO2 weigh, that could seem like a really weird question, and just by saying it, it seems weird to me. So let's think about this. If you have half of a dozen, you know that you have 6, right? So if you have half of a mole, how much would you have? Well, a mole is just a number. It's 6.022 times 10 to the 23rd of something. So if I had a mole of eggs, I would have that many eggs. If I had half a mole of eggs, then I would have this divided by 2, in which if you put that in your calculator, you would get 3.011. I should have been able to do that in my head. 3.011 times 10 to the 23rd eggs. The mole is nothing different than a dozen. So when you see something like this, don't let it scare you, okay? Because if I asked you, how many eggs would I have if I had 0.208 dozen eggs? So, okay, if you had 1 dozen, and you wanted to know what half of that was, you can multiply by 0.5, right? Because multiplying by 0.5 is the same thing as dividing by 2. So if you want to know how many eggs you'd have if you have 0.208 dozen eggs, all you have to do is multiply by 0.208. So 1 dozen would be 12 eggs, right? 12 times 0.208, and you get 2.496. So you'd have to chop up an egg and weigh it and do all that stuff to get it just right. But the idea is that the mole is nothing but a number, okay? So, now when we introduce the idea of moles of molecules, we have to think really carefully here. Because CO2 isn't, one atom of something. It's a whole unit like this. This carbon is in the middle, and there's 2 oxygens bonded to it. And if you have CO2, then it behaves as one unit like this, as with all molecules. So let's think about this. If you have a chocolate chip cookie, okay, and in this chocolate chip cookie you have 2 chocolate chips for every cookie. They're not very good cookies. You probably wouldn't want to buy these, but let's pretend that you do. So in every one, if you have a dozen of these cookies, then you would have a dozen pieces of actual cookie. And how many chocolate chips would you have total? Well, if you have 2 chocolate chips in every 1 cookie, and you have a dozen cookies, then you must have 24 chocolate chips, right? That just speaks to reason. So likewise, let's say you had a dozen molecules of CO2. Well, if this is CO2, and you have a dozen of these, this is COO. If I could do this a dozen times, but I'm not going to. You know that you'd have a total of 12 carbons and twice that many oxygens. You'd have 24 oxygens. So a mole is no different. It's just another number. So if I have 1 mole of CO2, I would have 6.022 atoms of carbon, and I would have 2 times 6.022 times 10 to the 23rd, I didn't say that before, 10 to the 23rd atoms of oxygen. Because you always have twice as much oxygen as you do carbon. Because no matter what you're doing, this guy stays the same. So if we want to know how much that many moles of CO2 weighs, we have to consider the difference between the weight of the carbon and the weight of the oxygen. So first thing I want to do is find out how many moles of each atom do I have. So since there's only one atom of carbon for every one CO2 molecule, then we know we have 0.208 moles of it. That makes sense, right? So 0.208 moles of carbon atoms, right? Just like if you had a dozen of these, how many carbons would you have? Well, you'd have a dozen carbons. So if you have 0.208 moles of these, then you'd have that same number of carbons. Well, what about oxygens? Well, it's going to be twice that amount, right? Because there's 2 oxygens for every 1 carbon. So I could take 0.208, multiply it by 2. I should have done this in my head, but it's 0.416. 0.416 moles of oxygen. Now, I could look on the periodic table and get my conversion ratios. So I know moles of carbon, and I can look on the periodic table, and it tells me that in 12.01 grams of carbon is 1 mole. Okay, so every 1 mole weighs that much. There's my conversion ratio. So now I can multiply. I want to get rid of moles. I want to put that on the bottom. And I want to go to grams, and conveniently, there it is. I put 12.01 at the top, and now just plug that. That's for every 1 mole. So now I'm just going to plug that in. 0.208 times 12.011, well, it's 12.01, but it's 12.011. Divide by 1, hit enter, and I get 2.49829. Now you want to trail out these significant digits, or you want to trail out as many digits as you can. But let's look back, let's think, how many significant digits do I have here? Okay, there's 4, there's 3, I'm limited to 3, so I'm going to keep a note of that. I want to do the same thing with oxygen, okay? 0.416 moles of oxygen. I'm going to look on my periodic table and get my conversion ratio, and it's going to say 16.00, or it could say 15.9994, whichever one you're using. Just plug that in. And that's going to give me 416 times 16.00 divide by 1, and we get 6.656. And this is grams. This is also grams, okay? Moles canceled, we had grams left over. Same thing there. Okay. Now, how many significant digits? We have 4 there, 3 there, so I'm limited to 4 here. Now we want to add these two together, because we found out how much they weighed individually, so let's put them together. And since we're adding, we have to line everything up. So 2.49829. I'm going to line that up with 6.656. And this was the last significant figure there. This was the last one there. So I'm going to be limited to that right there. So I'm going to plug all of this in. We don't want to lose digits. 49829 plus 6.656. And I get 9.15429. So this, on this side, is my last significant figure. And we don't need to round up. So my final answer is 9.15 grams.